Good day everyone, my name is Chiam Wei Xuan with matrix number 205677. Today I'm going to talk about fundamental first and second law of thermodynamics. This topic will touch on energy balance, energy change of a system, and also mechanism of energy transfer. The first law of thermodynamics, also known as the conservation of energy principle, is used to provide a sound basis for studying the relationships among the various forms of energy and energy interaction. The first law of thermodynamics states that energy can be neither created or destroyed during a process, it can only change forms. It is used to characterize the performance of cyclic conversion systems like fossil fire, steam power cycles, or geothermal cycles. So take a look at the picture here. So you can see that when the rock is at the top, the potential energy is 10 kilojoule, while the kinetic energy is 0. But however, when the rock falls down, the potential energy decreases to 7 kilojoule, and the kinetic energy increases to 3 kilojoule. This shows that energy changes forms. Dynamics can be used to explain adiabatic processes. During adiabatic processes, no heat transfer is occurred, but there will be several kinds of work interaction. So for all adiabatic processes between two specific states of a closed system, the network done is the same regardless of the nature of the closed system and the details of the process. So if we consider the network is the same for all adiabatic processes of a closed system between two specific states, the value of the network will be depend on the end states only, which correspond to the change of total energy E of the system. First law makes no reference to the value of the total energy of a closed system at the state, and the change in total energy during an adiabatic process must be equal to the net work done. So from the statement that we mentioned just now, the change in total energy during an adiabatic process must be equal to the net work done. The first example is the potato. When heat is transferred to the potato, the energy of potato will increase. Ignoring any mass transfer or moisture loss of potato, the increase in total energy of the potato will be the same as the amount of heat transfer. So if 5 kJ of heat is transferred to the potato, then the total energy increase will also be 5 kJ. So the second example, you can see that if 15 kJ of heat is transferred to the water from the heating element, 3 kJ of heat is lost from water to the surrounding air. The increase in energy will be equal to the net heat transfer to the water, which is 12 kJ. So here are some examples that also involve adiabatic processes. Situation 1, a well-insulated room heated by an electric heater. When electrical work is done, the energy of the system will increase. Since the system is adiabatic, so there will be no heat transfer occur, Q equal to 0. The electrical work done will be equal to the increase in energy of the system. Second situation is a well-insulated room with a paddle wheel. When stirring process happens, the energy of the system will increase. No heat interaction will occur as it is an adiabatic system. Shaft work done must show up as an increase of energy of the system. The third example here, in the absence of heat transfer, the entire boundary work will be stored in the air as part of its total energy. The energy of the system will be equal to the boundary work done. Will be applied on energy balance. Conservation of energy principle state that the net change, increase or decrease in the total energy of the system during a process is equal to the difference between the total energy entering and the total energy leaving the system. The formula is the energy in minus energy out equals to the change of energy of the system. Of a system involves the evaluation of the energy of the system at the beginning and at the end of the process. The formula is energy change equals to energy at final state minus energy at initial state, or we can say the energy 2 minus energy 1. The energy change of a system will be 0 if there is no change in states during the process. The first law says that the internal energy of a system has to be equal to the work that is being done on the system, plus or minus the heat that falls in or out of the system and any other work that is done on the system. So the general formula is the change of energy equals to the change of internal energy plus the change of kinetic energy and also the change of potential energy. So these are the three formulas that we can find internal energy, kinetic energy, and also potential energy. Now let's discuss on mechanism of energy transfer. First of all is heat transfer. Heat transfer to a system, or we call it heat gain, increases the energy of the molecules, thus the internal energy of the system. Heat transfer from a system, or we call heat loss, will decrease the internal energy of the system as energy is transferred out since heat is coming from the energy of molecules in the system. Next is the work transfer, an energy interaction that not caused by temperature difference between a system and its surroundings is called work transfer. Examples is like a rising piston, rotating shaft associated with work interaction. Work transfer to a system, or we call work done on a system, will increase the energy of the system, while work transfer from a system, or we call work done by a system, will decrease the energy of the system. Car engines and hydraulic systems, steam or gas turbines are some of the examples that produce work, while the compressor pumps and mixers consume work. Next is mass flow. When mass enters a system, the energy of the system increases as mass carries energy with it. So from here we can say that mass is an energy. When some mass leaves the system, the energy of the system decreases because the departing mass takes out some energy with it. Example, when some hot water is taken out of a water heater and is replaced by the same amount of cold water, the energy content of the hot water tank decreases as a result of mass interaction. So you can take a look at the photo here to describe the situation. So overall, for the mechanism of energy transfer, we can say that the net transfer of a quantity is equal to the difference between the amounts transferred in and out. The general equation of mechanism of energy transfer is energy in minus energy out equals to Q in minus Q out plus W in minus W out plus E mass in minus E mass out equals to the change of the E system. So all six quantities on the right side represents amount, so they are positive values. Since the formula just now is quite complicated, there's a simpler way to uh, simplify our formula, which is energy in minus energy out equals to the change of the energy in the system. And the energy in and out here is referred to the net energy transfer by heat, work, and mass, while the change of energy is the change in internal, kinetic, or potential energy. The formula can also be expressed in rate form, where the energy in and energy minus energy out equals to dE system over dt. For constant rate, the total quantities during a time interval are related to the quantities per unit time. So you can take a look at the formula here. There's a bit different for the mechanism of energy transfer in a closed system. For a closed system undergoing a cycle, the initial and final states are identical. Thus, the change of energy of the system equals to E2 minus E1 equal to 0. So from the formula here, we can get the energy balance of the cycle, that is the energy in minus energy out equals to 0. So energy in equals to energy out. A closed system will not involve any mass flow rates in the boundaries, and the net work output during a cycle is equal to the net input. So W net work out is equal to the Q net in. Let us have a try on some example questions with solution. Number 1. According to the first law of thermodynamics in an isothermal process, so we have to choose one answer from the selection. The answer is C. In an isothermal process, it can be implied that heat added to the system is equal to work done by the system. So the explanation here is According to the first law of thermodynamics, change in internal energy of a closed system is given by the difference between the heat energy added to the system and the work done by the system with the formula the change in internal energy equals to Q minus W. In an isothermal process, temperature is constant. Temperature is a measure of internal energy of the system. If temperature is constant, then there is no fluctuation of internal energy. So 0 joule equals to Q minus W. That means that it can be implied that heat added to the system is equal to work done by the system, Q equals to negative W. Question 2. A reaction at 1.76 atm produces 22.8 liters of a gas and involves 71.0 kJ of heat, which is endothermic process. Calculate the change in internal energy of the system in kilojoule. From the question here, we know that the pressure during the reaction is 1.76 atm. The volume of the gas produced is 22.8 liters, and the heat energy released by the system is negative 71.0 kJ. So according to the first law of thermodynamics, the change in the internal energy of a closed system depends on the heat exchanged by that system and the work done on or by the system by the following equation, which is the change of internal energy equals to Q plus W. So here we can know that the work done on a gas during expansion or conversion under constant pressure is given by the equation W equals to negative P to the change times the change of the volume. So we have to modify the first law using the above equation. We get that the change of internal energy equals to Q minus pressure times the change in volume. So plugging in the given values, the change in the internal energy during the given reaction is computed as follows. So at last we'll get negative 75.1 kJ. This is one of the example I took from our textbook, which is the cooling of a hot fluid in a tank. A rigid tank contains a hot fluid that is cooled while being stirred by a paddle wheel. Initially, the internal energy of the fluid is 800 kJ. You can refer to the picture here. During the cooling process, the fluid loses 500 kJ of heat and the paddle wheel does 100 kJ of work on the fluid. Determine the final internal energy of the fluid. Neglect the energy stored in the paddle wheel. So first of all, we have to make assumption. The first assumption we make is that the tank is in stationary state. So the kinetic and potential energy change are zero, and therefore we can get that the change in energy of the system is equal to the change of internal energy of the system. So the second assumption we'll make is energy stored in the paddle wheel is negligible. So from the analysis, we take the contents of the tank as a system. This is a closed system since no mass crosses the boundary during the process. We also observe that the volume of a rigid tank is constant, and thus there is no moving boundary work. The heat is lost from the system and shower is done on the system. So by applying the energy balance on the system gives where the energy in minus energy out equals to the change of the system, and we get the shaft work done in minus the Q out equals to the change of internal energy, which is U2 minus U1. So 100 kJ minus 500 kJ equals to U2 minus 800 kJ. So we can get the U2, the internal energy is 400 kJ. Therefore, the final internal energy of the system is 400 kJ. Now let's go to the second law of thermodynamics. The function of the second law of thermodynamics is to identify the direction of the processes. It also asserts that energy has quality as well as quantity. The second law of thermodynamics provides the necessary means to determine the quantity as well as the degree of degradation of energy during a process. It also determines the theoretical limits for the performance of commonly used engineering systems such as heat engines and refrigerators. This law is used to predict the degree of completion of chemical reaction and also define the perfection of thermodynamic processes. This law can be used to quantify the level of perfection of a process and point in the direction to eliminate imperfection effectively. There is the fact that certain processes never occur suggests that there is a law forbidding them to occur. This law is the second law of thermodynamics. The second law of thermodynamics states that heat transfer occurs spontaneously from higher to lower temperature bodies, but never spontaneously in the reverse direction. So it deals with the direction taken by the spontaneous processes. If the processes can go in only one direction, then the reverse path differs fundamentally and the process cannot be reversible. So there are two examples here where a cup of hot coffee does not get hotter in a cooler room, or transferring heat to a wire will not generate electricity. Like what I mentioned just now, the second law of thermodynamics is applied at heat engines, which is a system that performs the conversion of heat or thermal energy to mechanical work. The heat transfer from the hot object, or we call hot reservoir, is denoted as QH, while heat transfer into the cold object or cold reservoir is QC. And the work done by the engine is W. The temperature of the hot and cold reservoirs are TH and TC respectively. So we take a look at the picture here. For the A, the heat transfer occurs spontaneously from a hot object to a cold one, consistent with the second law of thermodynamics, while for the B, a heat engine, represented here by a circle, uses part of the heat transfer to do work. The hot and cold objects are called the hot and cold reservoirs. QH is the heat transfer out of the hot reservoir, W is the work output, and QC is the heat transfer into the cold reservoir. Because the hot reservoir is heated externally, which is energy intensive, it's important that the work is done as efficiently as possible. So we would like W to equal to QH, and for there to be no heat transfer to the environment, QC equal to 0. But unfortunately, this is impossible. The second law of thermodynamics also states, with regard to using heat transfer to do work, it's impossible in any system for heat transfer from a reservoir to completely convert to work in a cyclical process in which the system returns to its initial state. A cyclical process brings the system, such as the gas in the cylinder, back to its original state at the end of every cycle. Most heat engines, such as reciprocating piston engines and rotating turbines, use cyclical processes. The second law, in its second form, clearly states that such engine cannot have perfect conversion of heat transfer into work done. So that's all from me. Thank you.